probably going to work out a little bit better than the last one. And as I said before, sometimes some of these multi-choice have got a little bit of maths in them as well. So that might make 12 questions or something like that. So it's important as I'm going through to indicate to you guys that, you know, that area of the notes is where I've taken the question. At least you can get an opportunity to maybe print it out and circle it or copy it and put some sort of explanation mark beside it. So I have the assignment and I'm going to show you that shortly. So you've had your little break, 2 weeks. So you can have another break if you want to, but I would suggest that ripping into it's always the best way with mine. First up, so we'll give you that. You can't do it all straight up. Sorry, you can't go home tonight and finish it. Well, if you do, it's a bit of a miracle because we won't have covered the steel or the timber side of things for a couple more weeks. And as you note, the timber is the week of the hand-in, so there are only a couple of things you need to do for the timber on your assignment, and I'll probably be able to answer that if you ask before the notes anyway. A great deal of the first part of assignment 3 is concrete. Probably 10 marks out of 15 is to do with the concrete side of it. So, oh no, probably about 8. So there's quite a bit of marks involved in today's lecture and today's lab. I don't feel like being here today, but I thought if I do that, if I don't come in, it's only going to create issues to you guys to further down the line. So I'll do my best to get through everything, and we'll do my best to give you the example that we'll go over in the lab, which will be a worked example. It's a retaining wall, and there are a lot of things in that are in the test, and there's a lot of things in that you'll be able to work out your assignment from too. So like most things in engineering, we'll give you an example. The assignment won't be the same. You're going to have to apply your learning to the assignment. Okay? So there will be some things that I will say in email land. Have a look at the example and try and work it out yourself. There'll be other things where I can give you a little tip in moving forward. Just like the last one, really. And yes, we sort of progress forward just like the last one, and we do our test in the last week, just before hand-in. Queen's birthday is after the last hand-in, so for some of you that are only doing, say, 4 subjects, it's quite good. You'll get this one over and done with before Queen's birthday, and you can get on with studying for exams and stuff. You'll have that extra week up your sleeve for the other 3 subjects. So we've finished 50% of the course. You're not going to finish 50% of any of your other subjects until week 13. So that's kind of how this is so crammed. I get a lot of complaints every year about the amount of work. But if you look upon it with no exam to do, it's quite a different kettle of fish. So, yeah, I've kind of breezed over a couple of things with assignment 2. The next question that you're all wanting to ask me is, when will it be ready? Probably start looking at Moodle towards the end of this week. Okay? Maybe Wednesday, maybe Thursday. See how we get on. And it'll come with an example answer which has been quite manipulated this time by me. And it will also come with a whole pile of columns with a lot of stuff up the top that you should have actually completed to get full marks. So you'll be able to work your way through and see where you lost marks or gained marks. So assignment assignment 3 and 4. What are you actually doing? Well, the clue was in assignment 1 and 2 really, but I'll make it available now to anyone, and I'll make the notes available as well to anyone that's actually got their laptop or following this online. So right, assignment, I won't do that one because it's not ready yet. Show. Digital Dropbox. And the rich notes. Okay, so assignment 3 and 4. To help you, I've done a 3D drawing and a 3D sketch of what it should look like. We'll have a quick look at that now. Desktop somewhere. PC. Save. Fairly basic 3D drawing. When you zoom in on it, you can see that there are some angles, etc., joining the members on. This piece here is timber. There's a timber ridge board and 2 timber rafters. There's timber purlins. Then you've got your steel, which is down here. You've got a steel plate that's welded onto a column. Talk about all this in our notes section. There's a steel plate at the bottom. You'll be designing these plates according to some of my notes that you'll get next week, and you'll be putting bolts in them, bolting them down through into the foundation. This is nothing like any other assignments I've done before. You'll see the foundation slab is quite separate to the piles. So in elevational view, on elevation will look something like this. Notice, I'm only going to say this once. I've used some non-traditional ways of calling up everything. Ingrid would probably have your, as they say in New Zealand, guts for garters. In other words, she would beat you up if you did your arrows and leaders like that. Please do not copy mine, like a lot of you did in the assignment with a couple of things. I'm expecting these notes to be lined up and not hickledy-pickledy like my ones are. And I expect the leaders to be in the right place. In this case, this leader goes downhill from the top, which is incorrect. So you either move the note down and aim it upwards, or you do it from the bottom of the note. If you're unclear where an arrow should be, please ask me. This arrow is incorrect because it's pointing upwards from the bottom. This is incorrect because it doesn't have a leader line to it. So there's a lot of really bad dimensioning in arrows. Mine's a sketch to tell you what you want to draw. Believe me, in my working career, engineers from Auckland University with master's degrees and what have you, you would get a lot worse sketch than this. It would be on a piece of them in paper, and they'd say, guys, this is roughly what I'm thinking I want to do. You go away and design it and make it work. All right? Now, you don't copy what they've written on the back of a bit of toilet paper. You do it properly and regimentally with the drawing standards that the company asks for. So there's one view of it. Now, it looks easy, but it's not a case of just copying it. There's a lot of call-ups for the timber, which you'll learn about, steel, which you'll learn about, and the concrete call-up may be slightly different to what the way I've called it up as well. Reinforcing ones. There's also a table down here, which a lot of students email me in week 1 going, I don't know what the bend radius is. What's the minimum lap? You haven't given it on the assignment brief. Okay? diameter, minimum lap, 90-degree bend allowance, bend radius, and the mass. We will talk about all that in the lab, a little bit in the lecture, but you will understand that by the time your lab's finished this week. Notice there is a lap here. Now mine is only a sketch, so when you get something like this where the bars bend both ways, what that actually means is the bar goes to the absolute maximum that it can go to, and one's in behind the other. I'll explain that to you in the lab as well. So don't take that literally as being one bar in front of the other. It is one bar behind the other. With reinforcing, look, it's no different than your grandmother when she taught you how to do some knitting. Some sewing, all right? Not that mine ever did. It's embarrassing if I say that. What did she say when you were sewing something? As far to the edge as possible, all right? All right, if you're sewing a purse, it's no use sewing it up the middle. You're not going to get any money in it, are you? For all you guys that carry purses around these days. Not really my thing either. So with reinforcing, it's the same. To make something strong, you put the bars as far to the edge as possible. All right? As far to the edge as possible. So if I tell you the minimum concrete cover is 40, you push the bar right up against the 40 where possible. All right? Once again, I'll cover that in the lecture. But I just wanted to be sure that you knew that even you guys, with the modern age now, you all zoom in on your PDFs to sort of like 0.5 millimetre, and then you start picking me up on what's right and what's wrong. It's important that you understand that this is very much a sketch, and exactly where your concrete should be to the outside edge. So you'll see that in a number of places. Where it says lap, okay, should be in the middle. Bang on in the middle. And you know what? If you do it in the middle, that means both bars either side will be exactly the same. So therefore you can only have to call up that bar once. But don't forget to count it as 2 each time. So I get students that go, well, hold on, I've just been online, and the minimum length bar that you can buy is 9 metres. If you lap that in the middle, you're going to lose a lot of money by the time you finish doing the job. That's correct, but that's taking it a little bit too far. In the real world, they tend to look at what bars are available, and they make it work. I did a job in Indonesia, way up in the mountains, and we did a perfect design, and then they said, oh, the helicopter's just dropped off all the reinforcing, it's the wrong size. So we had to redesign it for the size of bars that were there and use those. That's fine. But in this job, working for me, doing this assignment, please assume that the lap is in the middle and there isn't any minimum size bar that we're ordering for this job. The seats, you'll notice, aren't on my 3D, but if you want to, for extra 3D marks, you can put a number of things on this job. I'm going to give you 3 marks for drawing up what I've done, and I'll be helping you through that. But the extra 2 marks is your choice. You can do bolts, lag screws, welding, outside sheathing, roofing, windows in it if you want. Just something a little bit extra on 3D. And if you want to go a bit further, you know, seating would be another thing that you might like to have a look at, along with putting the civil details on there. Remember, we had a platform and a cut, and we've got fill coming down to a creek. You know, you can go as far as you want with this. It's actually fun, the 3D, when we get around to it. In fact, you're going to be sitting there like you're playing PlayStation games going, you know what, this isn't really work, I'm enjoying this. And I don't want, it's only 5 marks, I don't want people spending like hours after hours doing it when you've got that wonderful geotechnical homework to please get on with your geology. It's much more important than doing 3D drawings. This is only a taste. Semester, either the summer break or the semester after that, you can do the modelling course if you pass this one as an elective on the diploma. On the degree, students will have to do it as a compulsory, and that will start straight away with 3D, and everything you draw will be in 3D in both of the programs, and they will be making you do schedules and quantities from those 3D programs. We will have to manually calculate the schedules and quantities today for your assignment, but the good thing about learning how to do that, when you're doing the modelling programs, you get an idea that something could be wrong or something's right when you're modelling something up. So it's a natural progression. Excuse my rather weird characters, they're the only ones I could find online, but never mind. We put a lot worse ones in there. I haven't completed the elevational view. I've given you a bit of a clue of what it should look like, but you're going to have to complete that yourself to get full marks on that one. It's an elevational section, which means somewhere along the line we've taken a slice through in the other direction. To me, that's the trickier one to do compared with the two sectional views. I've also provided, I can't show you here, but I've provided the 3 steel members, which we'll talk about next week in next week's lecture, and also next week's lab. We'll also talk about the steel members, but there's a little drawing there. I don't want you to use this drawing as a start for your assignment. I want you to start your very own drawing. There will be marks deducted if you use that drawing as your start drawing. So just what I want you to do is start a drawing in AutoCAD, bring in the title block, set it to A1 just like you were taught in the semester, at the beginning of the semester. And also put the logo in there, which I've provided, and then start drawing up the foundation slab for the concrete and the piles in plan view, and then of course later on for assignment 4 you're going to be doing the sectional views that you just saw. So what is the assignment? Well, it makes a bit more sense now with this drawing here. This is only a rough idea of what we're trying to achieve. Marae guest shelter, which a lot of maraes have that because they make the people wait until they're presented with, I've forgotten the name of it now, so I won't embarrass myself. There's like a stick that they put on the ground, and then the person accepts it as a challenge and they're invited into the marae. And while they're waiting, we all know what New Zealand's like, especially those in Rotorua at the moment. It can rain just a little bit, and this is quite a common thing. Amazingly, they don't have one of these at Unitec, but anyway, this is what we're supposed to be sort of designing. Forget about the wood carving and all that side of it. We've done it slightly differently, as you'll see. And it goes into what has been provided on Moodle. And assignment 3, which is due 20th of May, not that far away, 3 weeks. We have a plan view, which after today's lab, you should be able to ace that fairly quickly, in my opinion. It's probably the easiest reinforcing that I've had in 14 years here at Unity. So I'm hoping you should be able to do that plan view relatively easily. However, what goes hand in hand with that is the reinforcing schedule. Where's that gone? Bar schedule. That's the calculations behind it all. Once again, if you're on a roll, you might be able to complete both of those after today's lab. That's 10 marks. If it's getting a bit too tricky for you, then you can have a crack at the concrete quantities, materials, etc. So those that are in engineering in the field, or even in surveying in the field, may find that a lot easier. It's working out the quantities of the concrete slab and everything, as well as some of the materials that we're going to be using. That's also worth 5 marks. So that part of it is, I've made the first part of the assignment relatively easy and relatively easy to complete. There's not hours and hours and hours of drawing time in that. The second part is different. The second part of the assignment, which is due about 2 or 3 weeks after that, on the 3rd of June, is broken down into that typical section you saw. Pretty much doing that drawing, but doing it properly. The sectional elevation is another 4 marks. And I want you to do 2 details. As part of this course teaching steel, it's important that you guys know how to do a detailed drawing as well. It's only worth 2 marks. A detail is a blow-up, like if you've got a magnifying glass and looked at something. So it needs to be at a different scale, 1 to 5, which is quite a big blow-up. And you can't just put it on another viewport. It's got to be part of those two drawings you saw first up. I've been quite specific as what I want. I want a plan view looking down on the steel plate. And so therefore you're going to have to come up with a plate size that works. You have to wait until week 2 for that. And also you're going to have to come up with a detail where the roof purlins are connected at the top there. So once you've drawn it, it should be relatively easy to detail it. Sort of things I'm looking in the detailing: the welding symbol, the distances to the bolts, the overall size, and the hole size, I guess. Where it's and the bolts that you're putting in. One of them is Dynabolts, the other one is, I think, engineering bolts or something similar. Actually, I think it might be a different type of bolt to the engineering bolt. Anyway, we'll get back to that later on. The last thing is the 3D sketch, and that will take time. That will take some of your time, and if you're going to leave that to the last weekend, you won't get it finished, and it looks a bit weird when students don't finish 3D, because they leave things, it's like the meteorites that hang around in space. They leave a purlin over here and a beam over there, and there's something not connected there, and it looks really weird if you don't leave yourself enough time. So from my marking point of view, you're not going to get very many marks. So if you're going to have a crack at the 3D, leave yourself plenty of time to get it looking good. For a lot of you, this is the engineering, the reason why you did engineering, or probably not survey. The first section was the reason probably for the survey. But for a lot of you that are good at structures, this is the kind of reason why you're doing it all. So I try and put it out there with everything that you may need on the drawing, and it's going to be up to you to decide what you do and how you detail it. So there's a couple of hints here telling you to start with an A1 drawing, a full bleed, logo. The text heights is all written there, and of course a reference to the notes that you'll need. So, That's it. And just like the civil notes, there's about 50 something pages of structural notes as well. Which isn't unusual, it's sort of in line with 63 pages away. I'm pretty sure there's no lecture break this time around. Except for, okay. So this time around we're doing test revision here on the 21st of the 5th. But we don't actually do the test until the next week. So you'll have a whole week to digest the lecture before the test. And then there's no lecture the following week, but of course we've got the structural test. We've also got an extra portfolio drawings class here as well. So, I'm not going to read through these notes word by word. I'm going to point out the things that are important, and hopefully you can write down at the time with a bit of an asterisk or something like that beside it where I've got a question. So, when we specify concrete, we specify it in terms of its strength after 28 days. Not a month, 28 days. That's really important, and it should be one of your first notes on your concrete drawing. And it's also one of the questions in my test. Next question in the test is the difference between plain concrete and reinforced concrete. Where would we find each of those? The answer is plain concrete will be found in places where it wasn't that important to reinforce it. So you could have footpaths and limited driveways. You wouldn't want to put plain concrete where you're going to have trucks. So if you think that trucks are going to come in there, you need some of that mesh or some form of reinforcing. Curb and channeling is done without reinforcing. Stepping blocks, that should be stepping blocks, not steeping blocks, without an edging. Reinforced concrete is used mostly for most types of concrete jobs, especially those to do with structural. So you have reinforced concrete driveways, retaining walls, footings, building foundations, bridge piles, capping, slabs and abutments are just a few examples. I've pretty much worked with and drawn up most of those in my time. You end up working in a structural office, depending on what works around, you're going to end up doing that sort of work. For example, they're talking about a new light rail system around Auckland. Well, that's going to involve bridges, most likely footbridges and what have you. And they've got exactly the same things as normal road bridges. You're going to have piles, foundations, etc. and someone's got to detail them and someone's got to draw them up. If you're working in a company that's a big company in Auckland, you'll be using Revit, which also has a reinforcing steel program attached to it. If you're working in a small company, you'll be doing it on AutoCAD, drawing it pretty much 2D drawings. That's what a reinforcing bar looks like. For those that are doing engineering and doing materials second semester, you're going to get to actually grab one of these and hold on to it. Pretty big bars. Ingrid's got a selection of them. And they have these ribs on them for a reason. It's one of my reinforcing, one of my questions to do with concrete. The reason is, if you've got concrete bound around it and you've got an earthquake, if it had a smooth edge, it would just go slide across the top of it. If you've got an earthquake and you've got those ribs on it, you'll find it'll glue itself and hold itself to the concrete a lot better. For those that are doing structures, one of the big rules about concrete is that it resists compression. But we do need to reinforce it if we're going to put it under tension. Here's some examples of reinforcing cages. So surveyors need to take note of this because it's not unusual for surveyors to be sent to site to do a survey and be told to count the bars on a reinforcing cage. We're talking about a company that's got surveying and engineering as part of their company. Why would you pay for an engineer to go to site at the same time as a surveyor if you can get them to count the bars? Now, it's funny because that could well be your very first job out on site. And it's an important job. And if you go home to a place like, I don't know, maybe India or Turkey or somewhere in the third world, those reinforcing bars are worth a lot of money. So if the contractor can sneak one out without anyone seeing, they can use it on the next job. Alright? Some parts of China as well, some parts of the islands. It's all the same. The contractors are there to make money. If you can actually not put the right amount in, not put the right size bar in there, you can charge the client for it, but of course it's not in there. What's even worse, some of those buildings that fell down in the last earthquakes in Turkey, they discovered that they were supposed to have reinforcing in it, but obviously when the inspector disappeared, the whole lot disappeared on the back of a truck for the next job. So in New Zealand it's different. If you're on 60, 70, 80k a year, why would you steal a reinforcing bar worth, I don't know, maybe $5? You know, it's just not worth it. It's like going and robbing a dairy. You don't do that sort of thing. It's not worth a lot of money. But over there where it's worth maybe a couple of weeks' wages, you might start thinking differently about one reinforcing bar. In New Zealand, we tend to over-design. It's a very earthquake-related country. Even in Auckland, we can't get away with the threat of an earthquake. So when an engineer designs a concrete structure, it's important that those gaps and the number of bars are exactly as per the design. You take a couple of bars out, you've suddenly reduced the possibility of that standing up where it is. So yes, that was one of my first jobs. Go to site, walk past the guy who's about as tall as what he is wide, that does the reinforcing, and looks like he's going to bash you over the head with a bit of reinforcing if you pick him up on not enough bars, and count the bars and take it back to your boss who decides whether the concrete floor can go ahead. If any of you were watching the motorway structures over here at Waterview, a couple of years ago when they were going ahead, you would have noticed this type of reinforcing for the big circular columns. And what they tend to do is they will overlap one cage with the previous cage, wire it all up, slide this thing here upwards and do the next pour, and so on and so on. So if you have got different pours going on, it's important that there's a piece of reinforcing goes into that pour with an overlapping piece of reinforcing starting the next pour. Often you'll see little wee hats on top of the reinforcing as you drive around Auckland. That's pretty much so that what happened at Marsden Point doesn't happen ever again in New Zealand, which is somebody fell from a relatively small height, but doesn't take much more than that to end up with the reinforcing going straight through you. So they're pretty much protecting that from happening. Yes, it would hurt if you had one of those caps, but it wouldn't kill you, unless it was from that 8 stories high, I suppose. Mass concrete. Mass concrete is mostly used on the likes of the dams. I had the privilege of working on the Clyde Dam in New Zealand. There's been many big dam structures over the years, and that was a mass concrete gravity dam. So you're pretty much just using the weight of the concrete to hold back the water, which works everywhere except for where it's being built on the fault line, which is what the Clyde Dam was built on. I've also seen the Hoover Dam, which is also a mass concrete gravity dam, which is a lot more impressive. It was massive. Other things concrete is used in would be these wall structures which lock into each other as well. And then there's what we call in situ concrete. Does anyone know what in situ concrete is? On site, yeah. On site concrete. So your structure that you're doing will be in situ. I know you're quite good at reading that, that's good. But having said that, that'll make a really good note for your structural drawing. Concrete to be poured in situ. Quite a few people woke up, others are just still looking at me, wondering what I'm talking about. Precast concrete. A good example of precast concrete like this is with beams and box beams for bridges. I had the privilege of seeing beams being put in place on a motorway job. They do it at midnight, of course, because that's when there's least traffic. And what these beams are is pre-tension. So what they tend to do is they tension the reinforcing, they pour the concrete, and then they let the tension off. So they're what we call precast beams, and they're extremely strong, and they're specifically for the likes of floor slabs, beams, and columns. They also do that with wall panels, and that's one of the ways that they can put up buildings so quickly, especially car parks. I don't know if you've ever seen a car park go up, but it goes up pretty quickly. They stand these wall panels up, one on top of the other, fairly quickly with a crane, and position them in place. Uni-Ts, twin Ts and Uni-Ts. An example of these would be Mount Albert Palisade. If you drive under there, look up, you'll see Uni-Ts and also twin Ts. We had a problem there when we were designing that, and that was to do with the height. We didn't realise the bedrock or the lava flow from Mount Albert had gone all the way down through that area, And so every time we took like 100 mils, we had to dynamite the whole lot even further, and it was costing more and more money until someone came up with the idea of using twin Ts, which meant that we could we had more room underneath than the Unity for cars to drive underneath. So we saved ourselves quite a bit of money by using twin Ts. There's an explanation there on tilt slabs. I haven't asked any questions on that, but it's more for your information. We get into reinforcing steel. So the most popular grade 300 reinforcing steel, this is a very important paragraph. I've asked a question on this. Grade 300 reinforcing steel can be welded, but needs care and the use of low hydrogen electrodes for the best results. Grade 500 is weldable only with special procedures. Generally, grade 500 steel is considered not weldable. That is the answer to one of the multi-choice questions. And the most used grade of steel in reinforcing in New Zealand is grade 300. There's also a multi-choice question. We talked about the frictional surface and how concrete needs to bond with the reinforcing, and there's an explanation to that in that paragraph there. The picture below shows the appearance of a typical deformed reinforcing bar. The deformations are usually raised ribs. So those ribs that I was talking about are on deformed bars. Usually longitudinal ribs and a pattern of transverse ribs at regular intervals. So where it says here that, this is for your general information, the minimum standard stock length of a bar is 6 metres. Most sizes are available on 9 metre lengths and the largest size sometimes stocked in 12. In the past, some of my assignments I've given you a minimum length and said please don't use anything else but this. In this assignment, there is no minimum length. Okay, you just need to calculate the length of the bars. Another form of reinforcing is welded mesh, used only on the likes of driveways. And that is one of my questions as well. Where would you find welded steel mesh? Formwork. I'll draw a little diagram here because it best describes it, because I do a question on this. So, this is a reinforced wall, and we have formwork is these two things here. This is what we call false work. And this, in New Zealand, is what we call boxing. So when someone says to you, go and take some measurements off the formwork, they're talking about these panels here, which preserve the natural width that you want your concrete to be, say a retaining wall. If someone talks about false work, that's what's holding that up in place. It can be all different ways that that's done. This is normally a peg in the ground, of course. And if someone talks about boxing, that's the whole lot. So if you're asked to do quantities in terms of formwork, you would just measure these pieces here, the flat face, and of course the two ends of the retaining wall. Someone was talking about the false work that you might require, they're talking about that, and if they're talking about the boxing overall, you need to calculate this plus the false work. Alright? So if you understand that, you should be able to answer a couple of multi-choice questions that I have lined up on that. Alright? Now on this assignment, I'm not asking you to calculate formwork, false work, or boxing. But in past assignments, I have. So if anyone's helping you that's a past student on this course or has done this course before, it's really important that you explain to them that there is no need for that on this assignment. Okay? It's amazing how I can understand, how I can figure out that students have had a little bit of help from a past student because they go boxing ahead with everything that they did on their own assignment and they forget completely about the fact that this one could be a little bit different. Cover. I briefly talked about cover before. There's a little diagram down here a bit further that the short abbreviation for cover is CVR, and it's the distance from the outside edge to the actual bar itself. Now that cover is calculated based on many factors. For example, is the concrete in the ground? Is it air? Is it near the ocean? Salt obviously is going to start rusting the reinforcing. Is it in New Zealand? It could be near a geothermal site, which is even worse. Is it in Hawaii near a volcano site? So all these things make a difference to how much cover is required according to the ground conditions or the air conditions around where you're building. So it will vary, and it sometimes varies from the side to the bottom. I have a class example which I won't be going over, which I will give you with the model answer, and you'll see that it's different cover at the bottom to what it is on the sides. So you're lucky, the one you're doing with me has got a consistent cover right the way around. And you're going, but you didn't tell us what the cover is. It's not in the assignment brief. No, it's not. Just doing a little bit of role playing here at the moment. But if you have a look at the assignment, you'll see that I think one of these has got it. All cover equals 50 millimetres. Alright? But you do have to look sometimes for these things. So some of these notes you can use. There's one for example, all cover 50 millimetres. I'm expecting quite a few notes on your drawings. What I don't want to see is There was one there somewhere that said students to use week 8, 9 and 10. No. Okay. That is not a proper note for the drawing. Assume all laps in the centre of the building. That is another good note as well. That one can be used. So some of the methods that they use to set, is they have things called bar chairs, which are quite different to what I was used to when I was growing up. They are not the sort of bar chairs I used to go. And they sort of look a bit like this, kind of weird. And the reinforcing bars will sit on these bar chairs that they make up, which is exactly the right distance apart, height-wise. I mean, they can also be sort of like that as well. And they'll tie the reinforcing, there'll be plastic bar chairs which they'll tie the reinforcing to as well. The other thing that they often have is spaces which in plan view they sort of look like this. They have a reinforcing bar will sit at the same distance. You might have bars coming along in this direction. You can also have spaces in the other direction as well. If you ever get sent on site and you get told that the minimum distance between the reinforcing bars is say 300, it's quite good to have a little stick or something with 300 measured on it, so you can go along very quickly and measure to make sure none of them are an uneven distance. So when you're calculating how many bars there are, when you're spacing them on your drawings, I don't want to see you go 300, 300, 300, 300, 300, 300, and then get to the end and there's a gap that big. I want to see you spacing them evenly from one side to the other, so you might end up with, say, 287.5 all the way along, because that's the way it will be done on the site. Pouring of concrete, another multi-choice question. What I've done is I've given an example of a job and I've asked you which method would be best to pour the concrete. So what they try to do is get the trucks as close as they can. Obviously, you can pour it straight into the job from the truck. If that doesn't work, then the next thing is a hoist or a chute. So you can only do that so far. And then you start looking at the likes of pumping it down a pipe or something similar. And then of course, as we go down through the options, we end up with a barrow or a bucket, which takes a lot longer. So the concrete will cost more, and you're going to have to pay for labour of people doing it as well as paying for the extra time for the truck to be there. Other things to watch out for is that concrete goes off pretty quickly. I know most of you have probably never had an experience of this before, but in my case, my father I was the only son in the family, so my father would say, right, we're doing concreting on a Saturday, and I'm like, oh, okay, Dad. And the truck would turn up, and by crikey, if it was a hot day, that concrete goes off pretty quickly. You can water it slightly, but so you've got to work the concrete, and it will just suddenly go off, which means it can't be worked anymore, and it's too hard. So those are the sort of things that you need to calculate when you're doing your job. Is it easy to get in there? Can I get in there and work the concrete? Can we get a team of people in there before it goes off, or is it going to be too hard to do it? So if you're barrowing that concrete, you know, that's going off the whole time while it's in the barrow, while it goes into place. Compaction. Of course, just because you put the concrete over the reinforcing doesn't mean to say there's not air gaps and all sorts of issues with the concrete. So you have to compact it. In a small job like a retaining wall or something, you might use sticks and everything to push it all down, or a steel rod. But in larger jobs, they'll use proper compacting machines. And then, of course, the helicopters, I think is what they call them, for preparing lovely smooth surfaces on building platforms or houses. So there's some standard terms there. A stirrup is something that's very sort of close to what you guys are going to be doing for your assignment. Stirrup tends to be either a square shape, rectangular shape, or a circular shape, and it tends to bind the main bars which go up or sideways together, and tends to be of a smaller diameter compared to the main bars. Now, this is something where students got confused last year. They read this note here that says the lat is normally 40D on plain bars and 32D on reinforcing bars, D being the diameter. Now that is a multi-choice question, so that's one that you need to remember. The 32D, because most of our bars are deformed, so the question is about the deformed bar. 32D. But on the assignment, whatever you're told the lat is what the lat is. So here, you're told minimum lat 390 for the 12mm and 520 for the 16mm. So don't do the 32D calculation, it may not work out. Use those ones there because that's what the assignment is telling you to do. However, in the test, I don't give you that, so you have to use 32D. All right?
How come your balance are different from the other ones?
My ones, whereabouts? In here?
No, I mean, you're going over it. It was like 6, 9, 12.
Barlegs up here. Okay. So what that's trying to do is give you the idea that if you're designing reinforcing, you have to be aware that when you ring up the reinforcing guys at Fletcher Steel or wherever it is, and you say, I've got a reinforcing job coming up, quite a big one. What have you got in stock? Normally their minimum is 6 metres, just like ordering anything, they have a minimum. Most sizes of bars, so most diameters are 9, but they do go in some cases up to 12. So if you're designing something, then maybe it doesn't matter if that building is 100 mil shorter or whatever, just so that it takes in the complete bar, so you don't have any wastage. Because reinforcing isn't that cheap, especially if it's, I don't know, a floor slab as big as this lecture theatre, it would be quite expensive. If you could design it to their 9 metres by 12 or something, or even with an overlap, so that you're using, say, 2 9-metre bars. So there's a little bit of kind of working out involved there, which I have in the past made students do. The good thing for you, you don't have to worry about that in my assignment. My assignment is, I think, roughly 6 metres by about, I think, 10 or 12 in the other direction, I've forgotten. But I'm saying to you, lap them in the middle and don't worry about saving costs, just work out the distance. So this bar here, for example, this one here where my arrow is, you might work out that that is a certain distance in that direction and a certain distance in that direction, and that's all you need to do. All right? It's not particularly hard maths, and as I said, it's one of the easiest ones I've got students to do so far, but that's all you require. I just wanted to point out the notes that in the real world we do ring up the suppliers and work out what's available. Also, there may not be any, say, 16 bars, they might be out of them. So you've either got to wait 6 months and tell the client, sorry, you're going to do it for 6 months, or you go, actually, no, I'll go to 20. Well, we'll pay a bit more. So you have to tell the client it's going to cost more, but you get the building tomorrow. So it's like anything, like bricks or steel as well. So when you come to do steel next week, you'll see there's a chart exactly the same. By the way, we're up to here. Lap distance is the distance lapping. It also comes into play if you've got a door. So if you have a door, for example, you don't have a door in your assignment, but there is a door example as one of my questions. You've got a reinforcing bar that goes like that, that and that, around the doorway. That is also called the lap. That is also the lap there as well. So if you were given, say, a 520 lap, that's how far you would do the bar each side past this bar here. Same in that direction. And in a window situation, exactly the same. The lap goes, that's your lap there. So it's not just lapping bars. However, when you come to the end of a piece of reinforcing, and it comes along like this and down like that, like your one does, some students last year carried the bar on until they got the minimum lap out of all of that. That is wrong. The bar will stop right there. However, if it is a very large end to a piece of reinforcing and your lap required is only that much, then that's your lap there. So in this case, this bar here will come along and go in there, but that is classed as the lap. Even although that might be under the sides, you're not in the bar back in the other direction. However, if it's a large distance, then that you only do it overlap for the amount that's required. You've got this situation in your assignment, so you only need to take the lap as being the minimum distance from there to there. Cranking is not used anymore, but I wanted to show you what it was, and I wanted to show you that that is not what I want to do. In fact, one of the questions in the assignment is cranking used anymore in reinforcing houses? So where we have a construction joint, just like I talked about before, we have a concrete pour, then they're going to pour a next layer and a next layer. We always have what's called a starter bar, which will poke up through, ready for the next concrete pour and join onto the next starter bar. So with concrete, often the quantities involve the excavation, which will be the digger coming in and digging out whatever dirt or soil is required to be removed. The hard fill, which is normally put down under the concrete. The concrete itself, the reinforcing and the boxing, which would be holding the boxing would include all of that. Okay? So when you become one more step from where you are as a junior engineer and you're on site with an intermediate engineer, you'll be required to work all those figures out on site. So it's important that I explain this to you. When you get into your final year of engineering, you'll be doing a lot of this type of work, working out how much it's going to cost to do a concrete job. So I've talked about the boxing and the false work and the formwork, talked about the reinforcing that's in there. That's calculated in terms of weight, and I'll show you how that works in your lab today. And the hard fill is what goes underneath. So if you look at this here, you'll see there's a 500mm layer of hard fill under here, which will have to be calculated in, fairly easy calculation to do, which will also form part of your quantities. You don't have to do the boxing, and I'll show you that. I'll give you an example here of the quantities you should be doing. So I'll go back to this. There's an example of a schedule. So this is what I want your schedule to look like. This is the other 5 marks. There's 5 for the foundation slab drawn up, 5 for this. Sorry, this is 10 marks. 5 for this, and 5 for that. So with the materials, you're going to have concrete piles, hard fill, excavation. You don't need to do boxing, okay? So you need to calculate those. With the steel, we have a worked example that I'll be giving you next in your lab. Not this week, but next week. And with the timber's not too hard. You can work out the lengths of the timber probably without even doing the timber class. So you'll get that part easy enough. With the reinforcing in the concrete, you're going to have to fill out this schedule here. I'm going to go over one of those in your lab. Some students get it straight away, and others are sat there with their mouth wide open going, I really don't understand that. So, yeah, it's not a bad idea to possibly at least turn up to one of the labs, maybe 2. Can't guarantee you a seat, but I can guarantee that you can take some notes in there or whatever. So this is an example of what your 5 marks here for reinforcing schedule, 5 marks for that, and 5 marks for a plan view of this lab with the reinforcing in it. And that's 3 weeks to draw that up is a very reasonable time. It's not rocket science this side of it. And there's no reason why you can't advance the next part as well, because you start drawing up the 2 elevation views, but the 3D lecture won't be until about 4 weeks' time. And I'll actually, it won't be a lecture, it'll be in the labs, and I'll go step by step drawing up that 3D object. That's the notes. So here we have a typical way of calling up reinforcing bars. And we're going to get into more examples of this further down the line. I'm going to make an AutoCAD example available to you to have a look at, which will have the way of calling up the bars, etc. And as you can see by this example here, the 8 stands for the number of bars, so you need to calculate that. So, and the bar itself is this one here. Now it has a flat edge, so that means it doesn't bend, go up or down, it's just a straight bar, right? This circle is very important because that ties up that dimension line with the circle. And these 2 little bars at the top and the bottom are also very important. Those bars are called delimiter bars. And I think I'm going to put a question and add one this year because I've got so many people keep asking me an email saying, what's a delimiter? What's a delimiter? And so I think that deserves a question on its own in the test this year. And I will add that. It's not in there at the moment. The delimiter bar shows the extents of where this bar is going to go to. We used to draw this bar exactly in one of the positions, but in this case, you don't have to. Put it anywhere that suits. So I don't have to go anywhere up there. So this long bar here goes from that point to that point, and there are 8 of them. So the stele, and by the way, every stele that I've met in my life has been about this high and about this wide, and they've got like tattoos all the way down here, and they're built like outhouses, and yeah, they don't suffer falls. So if you do a drawing and it's wrong, they will let you know pretty quickly. I worked on site on the Clyde Dam. Our cages came down with the reinforcing on it, and the other reinforcing was sticking up, and if it didn't quite match, you could hear them down the hole, 100 metres away. And it was usually the F word followed by many other things, and you go, oh no, and then you would hear them coming along the office towards you, because they kind of thump as they walk, and then the door would open. Who did the drawings for section 66? And I'm, me. And it'll only be one bar that's wrong, but because it doesn't quite fit over there, they had to take the cage away, and he had to go down there and make it work, which often means bending it and cranking it and doing all sorts of things. So, and that was holding the, when that cage was down there, that was taking over one crane, and the Germans, of course, who ran the whole job, you know what Germans are like clockwork. I think they're racist here, aren't I? But is exactly what they're like, right? And if you held that cage down there for 10 seconds, that's half a concrete pour that they're missing out on. So if it was down there for a minute, they could calculate exactly how much concrete they were losing in time. And guess who got the blame? The stele. Guess what he was going to pass the blame on to the drawing. So it's really important that you draw these things so that the stele can understand it. It's dead right, and you don't get any of these numbers wrong. So that D stands for deformed. 16 is the diameter of the bar, and 01 is what we call the mark. So a mark is just a label. So the next bar will be 02, there it is there. So that one's a 12mm bar, it's not deformed. 02 is the mark, and that's at 300 spacings. And we've worked out that there's 20 of them. Right? Now, please take note. That is on top of the bar. That is on top of the bar. It's not on top of the reinforcing line. It's not way down here, which some students with an arrow to it. All right? It is on top of the bar. Now, that looks pretty straightforward. There's only 2 bars going in 2 directions. All right? Your assignment slab has got 1, 2, 3, 4, 5, 6, 7, 8. It's got 8 bars going in 2 different directions, and you must label them all without getting any of these lines through any of that text. You may put it through one of those. What I'm going to let you do. Alright? The reason is, if that line went through that number 1 and you printed it out as a PDF, you won't see the 1. And, like anything else, you'll pass that on to the steely, and he'll think it's a D6 bar. Right? So, your challenge isn't so much working out what this should stay and how many there are. Your challenge is jiggling it around on AutoCAD so that it looks right and there's no overlapping of anything. Okay? So what does that mean? Don't do it on the Sunday beforehand. Get this bit out of the road, because believe me, it takes a good half an hour to an hour to jiggle it so that it works. Because you move that bar down a bit, all the text goes with it, and suddenly it's in line with another line. Okay, so you move that line over there, and you move that up again, that one moves along. It's like playing that game where all the things come down and you have to put the boxes in. Alright, it can, you might fluke it, right? But probably it'll take an hour to jiggle it around. So do that early as you can, not on Sunday, because that is one thing that I do get rather annoyed at. There is a mark for getting that nicely positioned and getting all these things correct. And I also will show you in the lab a drawing that's been done like that, so you can follow it. By the way, these thicknesses are exactly equal to the 16mm bar. This thickness should be equal to the 12mm bar at each end. Okay. This is only a small example here. We'll give you a slightly better one as far as an AutoCAD drawing goes. Now, what I haven't said, but I will say, is that is always an open circle, about 2 times the diameter of the bar, approximately. Not 100 times, and not the same size, because you won't see it. Alright? So let's call it 2 times. What I don't want to see is that filled in as a donut. Because if it's a donut, that means the bar goes along and comes down and you're looking down on top of it. So one of your bars curves at the end. In fact, most of them do. So therefore, you'll need to do a donut at the end to show that it bends down. Because you're looking down on plan view. So that will have a donut here. Make sure the donut does not go past the edge of cover. Easiest way to do that, draw that as a P-line and offset it whatever the cover is. And then nothing will go outside it, right? Everybody signing a roll today, by the way? I haven't get it back yet. No? Make sure you sign it. They're getting a bit funny on it now. It's going to be electronic coming up soon. How about that? Exciting stuff. What next? So there's a little bit there on the procedure to draw the reinforcing bars, just a step-by-step thing. But I would suggest that you should be doing the drawing at the same time as you're working out the calculations towards the bars. So to work out the calculations of each bar, I'm going to give you a work example in the lab. In about half an hour's time, and then again on Tuesday, that'll help you towards your assignment, making a start on it. Once again, I've given some typical reinforcing allowances and tolerances. Please do not use this table this year. It's only examples, it's not for your assignment, along with the diameter of the bar in the deduction. I will show you the calculations that you need to do. Here is an official Unitec School of Engineering reinforcing schedule example, and I will show you how I want it to be done in the example this afternoon. Lastly, there's a whole lot of abbreviations that we're going to be using in structural, and I expect you to go through and have a look at them. If there's something that looks that you're not aware of, try and remember it. I have asked at least 3 multi-choice questions of that chart. So that's structural concrete. When you go on to do materials with Ingrid, it's going to be quite different. She gets right into making of the concrete, the rotting of the concrete, and the slump and all that side of things in your lab. And the notes are quite different. What I'm looking for is notes that should go in the drawing. There's a lot of material in there that you can read through and regurgitate onto your drawings if it's relative. Yeah, hopefully you can all make a good start during this week or weekend towards that first 15 marks. For some of you, there could be a little bit of a shock involved in assignment 2, but I can tell you that one student's still sitting on 49.5 out of 50, so he's still going to get that extra half mark to pass the course. The average at the moment seems to be around the 30 out of 50, so I'm hoping that those students can convert that into Bs with a bit of luck. So that'll happen later on in the week. That'll be sort of Wednesday, Thursday, Friday, right? Okay. By the way, for those people that were late coming in, if you think you're going to come up here and ask me questions, feel free. I've got a cold today, so come. Is the glass rolling somewhere?